You probably already know that carboxylic acid groups are one of the most important functional groups in organic chemistry. I'm James Wahlberg, and I'm here to tell you more about the properties of carboxylic acid groups. Let's take a look. The first thing to know about these groups is that there are two very different atoms in terms of their electronegativities, carbon and oxygen. That means that the carbonyl oxygen is not fully negative, but partially negatively charged, and that makes it a pretty good nucleophile. So there we go. You can see the distribution of charge in that carbonyl oxygen is mostly such that the electrons are on the oxygen. Therefore, if there is another species in a reaction that wants electrons, that oxygen can act as a nucleophile, and it might attack and start a reaction. On the other side of this picture, the carbon is electron deficient, and that of course means that it's a good electrophile. It loves electrons. So if there is a nucleophile somewhere in the neighborhood, then there's a good probability that that carbon could be attacked by that nucleophile. So understanding the electron distribution around that functional group helps us understand part of its chemical behavior. Another aspect of this group is that it has a hydroxy group. And one of the things about having a hydrogen bonded to an oxygen is that the oxygen is so much more electronegative than hydrogen that the oxygen will take the lion's share of those electrons and leave the hydrogen almost as if it's on its own. So that means if there is a negative or a partially negative charge group nearby, that hydrogen might be free to hydrogen bond with that partially negative group. One consequence of this for the carboxylic acid itself is that it can actually hydrogen bond with another molecule of the same acid and therefore forming a dimer. I'll show you that. So here we have a second molecule of the same acid, and each of these hydroxyl groups have a proton that is available for hydrogen bonding. Therefore, if two molecules of this acid come in close proximity, a dimer can form, and the dimer is held together through hydrogen bonds. Of course, a carboxylic acid is most fundamentally an acid, and that means that it donates a proton to solution, and when it does that, it becomes the conjugate base, or a carboxylate anion. Now, the strength of any acid depends on how good its conjugate base is at handling the negative charge that results when the proton leaves. In the carboxylic acid group, there is a way for the group to automatically handle that negative charge that results when the proton leaves. And that is that the highly electronegative oxygen atoms, one of which is already in a double bond situation with the carbon atom, can engage in a resonance structure. That is, that negative charge will become delocalized. And whenever you delocalize a charge, you automatically make the system more stable. To understand that a bit more, think of the reverse. Think about what happens when you take negative charge and concentrate it all in one place. Negative charges tend to flee from each other. So if we're able to disperse or delocalize that negative charge, that will make the system more stable. So that electron system in the carboxylic acid functional group allows for this delocalization and makes the conjugate base more stable. Now, it's possible that something else in the rest of the molecule might make the acid even more acidic. Say, for example, there is something highly electronegative, like a chlorine atom in this molecule. Now, through induction, because chlorine is such an electronegative element, electron density will be pulled away from the carbon atom, and that will allow the negative charge left behind when the proton leaves. That will allow that negative charge to be partially borne by the carbon as well. Let's look at an actual molecule and identify these functionalities. First of all, let's find the electrophile, or the thing that would love to find some electrons. Well, we have here a carboxy group in the end of this molecule, And recall that the electron distribution in these carboxy groups is such that the carbon tends to be electron deficient. If an atom is deficient in electrons, it would love to get a hold of some electrons, and therefore it is an electrophile. So the electrophile in this molecule is the carbon of the carboxylic acid functional group. On the other hand, if we want to find the nucleophile, the thing that would love to find some positive charge, let's recall that the carbonyl oxygen of the carboxy group is a locus of high electron density. Therefore, that oxygen can act as a nucleophile. If there is an electron-poor molecule in the vicinity, that oxygen would be prone to attack it and interact with it. Moving on, let's talk about the acidic hydrogen in this molecule. That, of course, is the H that's attached to the O in this hydroxy group of the carboxy functional group. But recall that besides electron delocalization that occurs within the carboxy group, this molecule actually has two highly electronegative fluorine atoms very close by. These will, through their inductive effect, withdraw electrons even more significantly away from the carboxylate anion, therefore stabilizing that conjugate base, which makes this acid even stronger than if these fluorine atoms were not part of the molecule. Finally, let's talk about hydrogen bonding in this molecule. Well, we do in fact have a hydrogen attached to an oxygen, so there's a hydrogen that's capable of hydrogen bonding, and we do have this carbonyl oxygen on the other part of the functional group, so we have the requisite properties for hydrogen bonding. Additionally, we also have another hydroxy group in this molecule, so the hydrogen on that hydroxy group would also be available for hydrogen bonding. So all told, there are multiple points in this molecule that could allow it to participate in hydrogen bonding. Well, I hope a walkthrough with that example helps you see where the properties of carboxylic acids come from. Good luck with your study of chemistry, and I'll see you in another video.